How to solve circuits the right way, once and for all. Hi, I am Vache Vorperian, and welcome to my course, The Joys of Circuit Analysis. In the first 5 videos, I showed you a very different approach to circuits than the traditional nodal and loop analysis method, which employs techniques of linear algebra. Those techniques are excellent for numerical analysis and are computationally intensive, not suitable at all for deriving meaningful analytical answers. It is now time to understand, derive, and generalize what you learned in those first 5 videos. This is the second series of my lectures based on my book, Fast Analytical Techniques in Electrical and Electronic Circuits, published by Cambridge University Press and available online from any bookseller. In this lecture, I will cover the essential fundamentals of transfer functions needed for the development of the extra element theorem. In this video, I will first talk about circuit structure, excitation, response, and how they are related to transfer functions. Second, I will talk about the 6 types of transfer functions of an electrical circuit. In the following video, I will talk about the determination of the poles of a transfer function and their physical interpretation, and the determination of the zeros of a transfer function and their physical interpretation. Imagine a linear time invariant circuit with an arbitrary number of nodes and branches, of which I'm showing 3 here. A circuit with no independent excitation in it is at rest, and we refer to it as the structure of the circuit. It is the structure at rest which determines the poles of the system uniquely. Think of the structure as a tuning fork or a bridge. And of all the bridges in the world, think of the Tacoma Narrows Bridge, which you most likely studied in your physics class and no longer exists, for reasons not much different than what makes a regulated DC to DC converter go south these days. Now let us look at how we can excite this circuit by an independent voltage source or a current source. One can excite a circuit by inserting an independent voltage source inside the branch or in series with an element of that branch. In this structure, we introduce a voltage source VT as shown in series with the resistor in the top branch. When we do that, voltages and currents appear everywhere in the circuit, and we say the circuit is no longer at rest. Each of these voltages and currents can be considered to be a response defining a particular transfer function from the applied excitation to that response. When we set the value of the excitation now to 0, that is to say, the value of the voltage source here, we set it equal to 0, all the voltages and currents will go back to 0, and we say the circuit goes back to rest. Now, a voltage source with 0 value is nothing more than a short circuit. And you see, when you do that, you recover the original structure. We can also excite the same structure or circuit by applying a voltage excitation directly across a branch or an impedance element of a branch. After all, it's your circuit and you can do anything you want. Here I'm applying an independent voltage source directly across the top branch or the top resistor. And when I do that, voltages and currents will appear everywhere in the circuit, each one of which can be considered to be a response, and I can define a transfer function from the applied excitation Vt to any one of these voltages or currents. However, there's a fundamental difference between exciting the structure by applying a voltage source directly across a branch versus inserting it inside a branch. And that difference pertains to the structure of the system, which determines the poles of the system. So pay close attention to this slide and the following slides, where I highlight this difference. So now when I set this excitation equal to 0, the voltages and currents everywhere will go to 0. And the circuit will eventually go back to rest. Just like that. However, we know that a voltage source with 0 value is nothing more than a short circuit. And when you do that, you replace the voltage source of value 0 with a short circuit. In this case, you end up shorting the top resistor inside the structure, and thus you modify the structure. It is important, therefore, to understand the difference in both cases discussed in relation to the structure of the system, which determines the poles of the system. Hence, we understand that all transfer functions obtained by inserting a voltage source inside different branches of the circuit, as shown here, will have the same denominator, because when we set the excitation to 0 in any one of these branches, you always get back the same structure. Likewise, we should understand all transfer functions obtained by inserting a voltage source in parallel with different branches will have different denominators, because in each case, when the excitation is set to 0, we get a different structure with a different branch shorted out. Very important. We'll now repeat this with current sources. Now a dual argument applies to current source excitations. When a current source excitation is applied across any branch of the circuit, the structure does not change, because when we set that excitation equal to 0 to send the circuit back to rest, being a current source, you open it and you recover the original circuit. And here it is, I am applying a current source directly across the top branch of the circuit. The circuit gets excited. I can define all kinds of transfer functions from this applied current source to different voltages and currents inside the circuit, get all kinds of different transfer functions, and they will all have the same denominator. Also, if I were to take this current source and apply it to the bottom branch and get all kinds of different transfer functions in the same manner, their denominator will be identically the same as the denominator obtained for all the transfer functions for the current source applied at the top branch. And that is because when I set the circuit back to rest by setting the excitation to 0, being a current source, this excitation, I open it. And when you open it, wherever it is, you're going to get back the original structure. In the same way, if I were to apply a voltage source inside a branch of this circuit, any one of the branches in the circuit, and obtain different kinds of transfer functions, the denominator of all those transfer functions will be the same, and they will be the same as those of the transfer functions obtained by applying a current source across any one of the branches inside the circuit. There you go. When you set the excitation to 0, the voltage source becomes 0, a short circuit, and you recover the original network again. Now something has to be made very clear, and that is the distinction between setting the excitation to 0 versus unplugging a circuit. And you don't want to get the two confused. This is what I'm going to talk about in the next slide. So finally, you must understand that Setting the excitation to 0 is not the same as unplugging the excitation source. This is very important because when we learn the extra element theorem and apply it to the determination of transfer functions, which are nothing more than a response over an excitation, as we'll talk about next, the extra element theorem will give you a set of instructions, and one of the instructions is set the excitation to 0. And you don't want to get that confused with unplugging the excitation. Instead, what you do is that you dial the value of the excitation down to 0. And if it happens to be a voltage source, you dial its value down to 0, which makes the voltage source equivalent to a short circuit. And if the excitation happens to be a current source and you dial down its value to 0, the current source acts like an open circuit with 0 value. And this is very important to keep in mind. I will now review the basics of transfer function as they pertain to the development of the extra element theorem. A transfer function, represented here with this block diagram for a linear time invariant system, is the ratio of the Laplace transform of the response of that linear time invariant system to the Laplace transform of its excitation, while all initial conditions are set to 0. So the block really represents a linear time invariant system here, in which we can have many different transfer functions depending where we excite that time invariant system and where we look at its response. Essentially then, the transfer function is the ratio of the response to the excitation in the frequency domain. So we write that Rs is the Laplace transform of the response, where Rt is the time domain response. We take its Laplace transform. And E of s is the Laplace transform of Et, which is the time domain excitation. And the ratio of the two gives us the transfer function, the definition of a transfer function. Now you learned in your system theory class that a linear time invariant system is a dynamical system whose equations are governed by linear differential equations with constant coefficients, from which it followed that the resultant transfer function is the ratio of two polynomials in the Laplace variable or the complex frequency s with real coefficients. The ratio of Rs to Es is the definition of a transfer function. And as it turns out, that transfer function can be written as the ratio of two polynomials, one in the numerator and one in the denominator. And this is what you see in most of your system theory class. However, we should point out now that this is not the best way to write a transfer function for any physical system, for reasons that I'm going to make very clear. A better way of writing this transfer function is to normalize the numerator and the denominator with respect to the frequency s, so that the leading term is unity followed by powers of s in the numerator and the denominator. This way, the constant that you get up front, g0, will have exactly the same units as the physical transfer function g of s. And the sole purpose of n of s and d of s is to tell you how the transfer function departs from g0 as the frequency increases. Does it go up? Does it go down? Does it go through a resonant peak? Does it go through a resonant notch? Does it stay flat? It's got to do one of those things. So G0 is a constant now which has the same units as G of S, which itself may be a high pass gain, a low pass gain, a mid-band gain, or a resonant peak or a resonant notch. I will give you various examples of these later throughout the course. N of S, as I mentioned, is a unitless normalized polynomial in S with leading term unity. Its roots are known as the zeros of G of S. Likewise, the denominator is a unitless normalized polynomial in S with unity leading term. Its roots are known as the poles of G of S. I'm going to demonstrate now with a very simple example what I was talking about in the previous example. Here we have a first order circuit for which we want to determine the transfer function from the voltage across R3 to the input excitation Vin of t. So we transform the circuit into its Laplace domain. Vin is replaced with Vin of S, L is replaced with SL, and V0 of t is replaced with V0 of S. And the transfer function for this circuit is written as shown here. AV0, the constant that appears up front, is nothing more than the voltage transfer function at zero frequency, which you can see immediately from the circuit is given by the parallel combination of R2 parallel R3 divided by R1 plus R2 parallel R3. And that's the constant that appears up front. This is followed by a numerator with leading term unity and a denominator with a leading term unity. So AV0, the constant that appears up front, is the value of the transfer function at zero frequency. It itself is a voltage gain. And it's a low pass gain. The numerator is a first order numerator, of course. It's a normalized frequency polynomial with leading term unity, and its root, SC minus R2 over RL, is the zero of the transfer function. D of S likewise is the denominator, a normalized frequency polynomial with unity leading term, and its root is minus R2 plus R1 parallel R3 divided by L. And from these two expressions of the zero and the pole, we can clearly see that the zero occurs before the pole, simply because the numerator for the zero is R2 and the numerator of the pole is R2 plus R1 parallel R3. So to summarize, the particular transfer function of this circuit can be written as follows. A constant gain AV0 and a numerator 1 plus s over omega z divided by a denominator 1 plus s over omega p. AV0 is the low pass gain of the circuit, omega z is the zero of the circuit, and omega p is the pole of the circuit. Of course, one could obtain another expression for this transfer function, which is entirely meaningless, but nevertheless very accurate, and it looks like this. And only the Lord knows how many times I've seen this expression in application notes, books, reports. It is an expression that makes no sense, but as I said, very accurate. It is of the form that you studied in your systems theory class. A0 plus A1 of S divided by B0 plus B1 of S. Not the best form for any physical transfer function, for reasons that should be pretty clear to you by now. Now we want to specialize the concept of a transfer function, which I have exposed to you, to the 6 possible cases that we can have in an electrical circuit. First, we speak of a voltage gain of a circuit. If you have an amplifier, it's typical to speak of its voltage amplification. It is the response of some output voltage V2 to an input signal V1, known as a voltage gain or a voltage transfer function. We can also speak of a current gain, in which you speak of a current in some branch of an amplifier, typically in the output, of course, to an input current excitation. Another useful transfer function of a transducer or an amplifier is its transadmittance or transconductance, where you study the current in some output I2 to an excitation V1 applied at its input. You can also study the transimpedance or the transresistance, in which you study the voltage at some output V2 to a current applied at its input. Now, in addition to the four well-known transfer functions that we just talked about, we add the impedance looking into a port of a network and its reciprocal, the admittance looking into a port of network, as two additional transfer functions of an electrical circuit. For an impedance looking into a port of network, also known as driving point impedance, we apply a current source and study the voltage across it. That is to say, the ratio of V1 to I1 in this diagram is the input impedance of this network. So if we are going to think about the impedance function as a transfer function, its excitation is only a current source. Its reciprocal, the driving point input admittance, is determined by applying a voltage source at some port and studying the current going into that port in response to that voltage V. That ratio is known as the input admittance. So if we are going to think about the input admittance as a transfer function, we have to say that its excitation is a voltage source. This distinction is important because, as I mentioned earlier, when we apply the extra element theorem to the determination of a transfer function, in this case an input impedance or an input admittance, then the extra element theorem gives us a set of instructions. One of them is set the excitation to 0. And you have to be very clear about what is the excitation of that transfer function for which you have to set the excitation 0. To summarize quickly then, we are going to learn how to use the extra element theorem to determine these transfer functions. To apply the EET correctly, we need to be clear about the excitation and the response of that transfer function. For the first four transfer functions, there is no ambiguity as to which is the excitation and which is the response. The excitation, however, for a driving point admittance, we should understand is always a voltage source, and the response is the current through it. And for a driving point impedance, the excitation is always a current source, and the response is the voltage across it.